bachelor's degree in physics from the University of Science and Technology in China in 2011. He then received his PhD degree from the Department of Material Science and Engineering at MIT in 2016. From 2016 to 2020, he was a postdoctoral researcher in Professor John Rogers' lab at Corey Simpson Institute for Bioelectronics. His lab research focuses on heterogeneous integration of soft materials and nanomaterials to design and develop devices for healthcare. He has won numerous awards, including Hettleman Prize, Neurosport Award, Biotech TRG Award, and Trax Award, NSF Career Award, Materials Today Rising Star Award, and others. Floor is yours, Professor.
Thank you. Thank you very much for the kind introduction, Professor Dr. Massey. It's a great pleasure to have this opportunity to speak in front of experts in this field. From the audience, I saw there's lots of familiar names. I look forward to the interaction afterwards and a future opportunity to meet you in person. So the research is about how we can design biomedical devices, specifically in the electronic space. And it's not only about the electronic design, but more about the materials, how we can design new materials. And also, importantly, is assemble the materials with different properties into a coherent devices that can operate for a single functions in the biomedical field. And then, as you probably know, so in the medical operations, so the medical doctors needs to use a device or medicines to interact with the patients at specific locations, either through the skin or at deep down into the body at certain organs. That requires the contact in certain way or form between the biological systems with the non-biological devices or materials. But biological systems are carbon-based. The materials has the freedom to make a non-carbon, especially to utilize those non-inorganic or semiconductor high-performance materials that can already establish in other industry, especially the semiconductor industry, to realize the certain functionalities. And also, especially for the future robots, is most likely also a non-carbon based or probably silicon based. So the interface will generate lots of challenges, and especially the materials levels. There's a lot of mismatch. The first example would be the mechanical mismatch. So here shows electrodes that inject into the brain, and the brain has a mechanics like a TOEFL, but the electrodes intrinsically for inorganic materials, it's several orders of higher in terms of the rigidity compared with the brain. So how we can address this tissue is another, the mismatch is another challenge. And the other is the surface chemistry, like showing as example of pacemakers. So over the period of the implantations, the surface will generate a certain immune response. It may be slow, but after a certain time, it could be years, it can generate fibrotic tissues. And those tissues can block the efficient transport of the charge from the device to the heart, which prevents the effective function, especially for the pacemaking process. So there's lots of materials questions required here to investigate. So in this research, we will talk about from the device perspective to address a materials challenge. So the first one is how we can structure high-performance materials, especially inorganic materials, such as the monocrystalline silicon. So if we can structure silicon in three-dimensional geometry, complex structures emulating the biological system, basically we can structure all kinds of other materials as well. And then we will realize the functionality of those 3D unconventional structures for biomedical sensing. And further, we will develop it into robotics that can behave as implants to address lots of challenge in the implantable space. And then we will focus on the drug delivery systems, how we can utilize a device platform and leverage the circuits, especially the microcontroller chips, to realize a digital manipulation. And further, we can enable the automation of such a delivery system. And the third one is a wearable sensor, specifically focused on the muscle tracking, how we can use in light instead of other field mechanisms compared with ultrasound or the electrical EMG to interact with muscle tissue in order to track the muscle contractions during the daily activities. So for the first devices, we first developed a transfer printing strategy that allowed the silicon nanoribbon to be transferred on a soft substrate with a hollow trench in the middle. So that way, we will be able to emulate a lever rule mechanisms that allows the travel of the plastic substrate over a long distance in order to manipulate the micro scale structuring of the silicon nanoribbon at the micro scale levels. And such lever mechanisms allow the manipulation over a very precise fashion through the long distance travel of plastic substrate. And the outcome would be the high degree of folding mechanisms that allow the silicon nanoribbon to be bent over 180 degrees, which is not being achievable by all the previous mechanisms. And this 3D bendy structure can be situated on a edge instead of a flat substrate. That would allow the functional components to be structured onto an unconventional device platform, especially for those non-flat medical casters. And what's additionally the interesting observation will be the flat top. So such a high degree of bending enable the monocrystalline silicon to generate a flat top on the arc, the top of the arc, which is not observed by other strained monocrystalline silicon structures, and which probably due to the high angle degree of bending. And this is not being captured by the FEA simulations. So we think these could be the overall structure curving along the width of the strips, as well as the interplay between the crystalline structure over the mechanical strain at larger scales. And then this observation is universal. So for a wide range of bending parameters or the width of the silicon strips, as well as the length, we can all observe a very interesting flat top on top on the top. This could generate interesting manipulation of the carrier mobility in the silicons, depending on the strain applied to the silicons. And beyond the single layer of silicon, we can transfer multiple layers of silicon nanoribbons on the trench. And that would allow us to structure the silicons into double helix structures, which emulating the DNA double helix structure. It's a sort of a bio-inspired design. And the finite element simulation could review depends on the all kinds of strain parameters beside the width and the length of the trench. The strain applied onto the silicons is well below the fracture strain of silicon, so which validates such a high degree of folding will not generate disturbing effects to the silicon structure overall. And then we can utilize such structural mechanisms to build devices. Here, we can embed the silicons into the biopolymer film, which is a polyimide, and structure them into these flower structures. And then it can allow the device to be enclosed in a medical canister. So we know for medical implantation, so there's a dilemma. So one way, on the one side, we want the device to be as small as possible, preferably using the medical canister. So that way we can minimize the tissue damage during the implantation stage. But once the implant reach to the lucky locations, so there's another preference, which is contradictory to the implantation. We want the device to generate a sufficient coverage with the tissue areas in order to generate effective therapeutic or diagnostic effects. And that dilemma could be a challenge. And these Bloomberg robots design mechanism could be a way to leverage such a dilemma. So by enclosing in a canister, we can minimize the implantation damage. After the canister reach to the target location, then the structure can extrude and expand like a flower blooming in order to generate the contact interface and fully cover the target areas. So in this case, we are making a cardiac canister to realize a real-time continuous monitoring of the cardiac output and the stroke volumes. So using an animal model, which is a rodent model, the heart is dramatically small. So we will be able to have a full span of the strain coverage over the heart through the canisters that allow multiple channel of monitoring the cardiac strain contract in terms of the contractility in order to differentiate the nuances in the local cardiac contractility. That can reveal the difference of the disease's heart in terms of local contraction, and we can see some area shows a more severe contraction damage than other areas. And then in terms of the normal heart contraction and the contractility are different depending on the areas, which cannot be reviewed by a single point sensing mechanisms. And then all those devices, as you could imagine, is passive, which means it requires an external mechanism to enable the structural reconfigurations. So we think whether we can use stimuli responsive materials into the microfolding process to enable a robotic mechanism for the implantable devices. And by achieving that, we envision there could be a certain scenario that can utilize such robotic transformations as implants. So the most representative example would be the cardiac patch. We know most of the patch, as shown here, are fabricated in 2 dimensions. It's a flat film. And then the heart is curvilinear. It has a very strong curve. And then in order to have the flat patch attach well to the heart, it requires adhesives. And as you could imagine, especially for mechanical engineers, even though the adhesion allows the intimate contact between the flat patch and the curvilinear heart, but it generates interfacial stress that's pulling the heart towards a more flat geometry. That interfacial stress can be a factor to disturb the biocompatibilities. And similar to other scenarios, so if we could design a cuff that can self-twist itself, that can alleviate the implantation complexities. So allow the doctor to implant the strips, the cuff easily. And then if we can design a devices that can expand its geometry in the stomach, that would effectively allow its prolonged stay in the stomach areas for sustained drug delivery and chemical sensing. And similar to the blood ladder, we can design a device that conform to the ladder, and no matter it's a change, the changing volume of the organs, and while applying the electricity and monitoring the volume to actuate the bladder clearance. And all those scenarios allow us to design from the materials levels, since the device requires both soft mechanics as well as miniaturizations for implantable scenarios. So in order to achieve sufficient miniaturizations, we were thinking skin-inspired soft robots. So that inspiration not only considers the sensory skin, but also consider the skeletal muscles, which located right underneath the skin surface. And that way, we can generate a materials continuity between the artificial skin, which embeds the nanomaterials-based sensors, as well as artificial muscle layers, which is based on the thermal responsive hydrogels. And that will allow a precise actuation depends on the local sensing observations in order to enable both miniaturization of the device as well as the high biocompatibility of the materials due to the matrix composition are based on the hydrogel as well as a biocompatible plastic, thermoplastics. And here we build such devices which contains both the actuation hydrogel as well as the sensory skin layers. And upon the contact with the tissue, which will elevate the temperature of the device, and that elevation triggers the contraction of the thermal responsive hydrogel in order to bend the device into a bowl shape that can hold the heart by itself. As you could see from the picture, so without additional interventions, the device can physically hold the device without adhesion layers. And that would minimize implantation complexity as well as generates intimate contact for more effective senses. And then the outcome will be a high fidelity monitoring of the cardiac contractions, and which corresponds well with the ultrasound monitorings. And then you could imagine how we can make the implant wirelessly operate. So here we provide a design of a utility on the near field communication coils, and that would allow us to build LC circuits, while the capacitors is encoupled with the pressure sensors, and the capacitive change which is a result of the external pressure change can lead to the resonance shift of the LC circuits, which can be picked up by the external VNA readout. And similar to the energy receivers. So if we apply a coil-based energy source that can efficiently transmit the RF energy into the receiver coils that connects with the implants in order to providing the energy to enable stimulations. In this case, it's a thermal stimulation based on electrode heaters. And here we show the implantable coils has a very high, sufficiently high energy receiving capabilities, which can heat up a thermal heaters, as shown from the heat maps, and that heating can effectively triggers the actuation of the muscle layers in order to bend the structures on demand. And so here, the first devices are mostly for the sensing, and as we know, for implants, also for the skin devices, the therapeutic capabilities could generate a broader impacts in the biomedical spaces. And we were thinking how we can utilizing a wearable platform to achieve a precise delivery of drugs through the skin or in a transdermal fashions. And it turns out there's a lot of critical clinical needs in this space, especially the drug additions, and that for those relevant drugs, especially the opioid, it heavily depends on the manual administration of those drugs. And then the users who administer drug could miss the optimized time point or miscontrol the dosage levels. Both of the situations lead to adverse effects. And so in reality, so there's more than 75,000 deaths annually associated with such overdose or misuse of the transdermal delivered opioid in the United States, and most likely, and those numbers are correlated with the working age population. So another case that can utilize such precise administration of transdermal drugs is the insulin for patients with diabetics. Also on the markets, so there's digital devices that integrates with a small pump to administer insulins through a long, thick needles into the fatty tissue layers. But as you could imagine, the device is relatively bulky. It's not very comfortable in terms of wearing. And there's a lot of adverse effects with such long needles due to the infection and inflammations. So to overcome all those challenges, we have designed a microneedle platform that can realize the digital optimizations or digital control. So in this way, we were considering how we can use connects a drug delivering system, a drug delivering reservoir with a microcontroller chips. And it turns out there's materials which it has been established in the previous research efforts represented by Professor Lanner's lab to utilize the nanomembranes of gold as a barrier to prevent the diffusion of the drugs from the reservoirs. And what's more interesting is upon small electrical triggers, which is around 2 volts, and it can effectively undergoes electrochemical corrosions in the biofluid environment. And such corrosion allows the barrier to disintegrate within minutes, maybe half minutes, to allow the barrier open and the drug to diffuse through the barriers and to enable the drug deliveries. And in that way, we will be able to build a wearable platform that can all be controlled by each microneedle through the microcontrollers. So you can imagine each needle can connect with a specific channel through the microcontroller. We can digitally programming the needle gate control switch at a specific time and upon schedules. And such a microcontroller can also connect with a digital sensor in order to optimize the delivery schedule and the dosage. And then from the experimental demonstration, you could see the deposition of the gold barriers on the microneedles can generate a very robust film to prevent the diffusion of the drugs. And upon a small coverage voltage bias, the gold will undergo electrochemical corrosions, and that will expose the drugs within a half minute. And upon 2 minutes, then the gold are mostly corroded away in order to generate a full speed of drug deliveries. And then another advantage to have the gold-coated layer is we can use a beam of laser to pattern the gold layers into the traces, and with each trace connects to a single individual microneedle, and then we can use a microcontroller to control each trace and manipulate its electrochemical corrosion schedules individually. So that would allow us to control both the time as well as the location of the drugs to initiate the diffusion purpose, and in order to realize the digital controls. And then we can connect the gold-coated microneedle with a Bluetooth microcontroller to realize a wireless design. So in this case, the microcontroller is powered by in a battery-free version through the NFC coils, and coupled with a supercapacitor, and in order to facilitate its availabilities without additional batteries that could generate a certain risk in terms of long-term wearing. And since the electrochemical corrosion only relies on a small voltage bias instead of the current dosage from the power source. So that significantly reduce the necessity of certain power requirements for the microcontrollers, so which allow the device to be powered in a battery-free versions. Then we can design the microneedle into a longer versions that would allow us to implant the needle into the brain of mouse, and to facilitate a collaboration with a neuron surgeon. And we first demonstrate the biocompatibility of the needles in the brain situations. And in this case, it has additional connectors externally, which can couple with electrical wires through the external controller equipment. And in this case, we can using the gold-coated microneedle both as an electrical stimulator when the voltage bias is operated below 2 volts, and which will effectively prevent the electrochemical corrosion. Or we can use it as a drug delivery reservoir when the voltage bias at a relatively higher levels that can corrode the gold, and in order to expose the drugs for diffusions. So the preliminary animal studies demonstrate the effectiveness of the gold layers to prevent the drug loaded in the microneedle to diffuse externally. So in this case, it's a melatonin, which is a sleeping drugs. And then we, as the animal study, we could see upon a small triggers, so the gold can effectively corrode, and that would allow the diffusion of melatonin, which allow us to observe a significant change of neural activity upon such electrical triggers from the living animals. And then, as you could imagine, the gold coating may generate complexities in the drug encapsulations. So those gold are mostly deposited through the sputtering or e-beam depositions, which requires a vacuum, and also it can slightly elevate the temperatures. And both of the condition is not preferred by certain drugs, especially those biological drugs. And to address these issues, we look into a different metallic materials. In this case, it's a 2D mixing that can be solution processable and to coat it on the microneedle with good uniformities. And among electrical triggers, the mixing layers will undergo a redoxing reaction in order to generate fracture due to the oxidation process. The fracture will disintegrate the mixing coated layers in order to expose the drug loaded inside for effective drug delivery. So here, once we have digitally controlled drug delivery systems, we will be able to build a closed loop biomedical devices that can leverage those digital sensors. So one typical sensor we can utilize is those optoelectronic systems. Traditionally, it has been used to measure the blood oxygenations and blood pressures. And in this case, we were thinking to measure the mechanical factor from the tissue, basically the muscle contractilities. So there's a lot of clinical needs as well as the rehabilitation needs from the real-time muscle tracking wearable devices, both for making the prosthetics to be more precise in terms of a control. If there's a device that can continuously tracking the muscle movements near the prosthetics, that would be a engaging point for the prosthetic parts to actuate, depends on the nearby muscles. And the other utility could be the rehabilitation process, where the patients with muscle injuries to optimize is a rehabilitation process much effectively, and especially due to a sudden change of the muscle damage from the hidden layers of underneath the skin, which is not easily observable from the outside. And there's a lot of existing devices that can enable the muscle tracking purpose. So one popular devices is EMG monitors and wirelessly operate through Bluetooth. As you could see from the picture, the device is relatively rigid, and the signals is confounded by enormous noise from the environments, as well as motion artifacts. And then the other technology is ultrasound, which can providing a high resolution imagery level of information to assess the muscle structures. However, the challenge here is there's a strong requirements of adhesion layers. Usually is a hydrogel between the devices and the skin. And also during the measurement stage, it requires the user into static gestures, and which will prevent such devices to monitor the muscle movement through the daily activities. And then the third, not very popular examples cases is implantable devices, which only be applicable for patients with a severe case of muscle injuries. Thus, it's not very scalable and universal for broad users. So then we look into different mechanisms. In this case, we are thinking using the near-infrared light, which has a strong penetration depth compared with other wavelengths of light. And this penetrates depth a few millimeters into the skin, would allow the light to reach to a muscle layers, skeleton muscle layers, to generate efficient light tissue interactions, and that would providing mechanisms to detect the muscle motions. And we carry on the multicolor simulations, which reveals the manipulation of a backscatter light from the muscle contraction to change the amplitude of the light scattered backwards from the skin. And that can generate, validates our device design mechanisms. And one additional advantage of the devices, so as long as the light can be injected into the skin, we will be able to provide effective sensing capabilities. So that would allow us less depends on specialized attachment factors between the devices as well as the skin layers. And then the light can be controlled in a sufficient low levels, which will prevent additional tissue damage. So we designed wearable devices and into a T-shape, which can be applied onto the neck. So the device has a 4 sensing pixels that features the near-infrared LED and photodetector coupling, and to detect the backscattered near-infrared light. And also the device features a gyroscope, which can be utilized to fit into the machine learning algorithms to minimize the motion artifacts from the user itself. And by tracking the neck muscle movement, we will be able to assess the coughing severity, as well as other swallow disorders that can all relate to the severe diseases such as COVID, dysphonia, as well as dysphagia. So all the sensing information can be fed into a machine learning algorithms in order to generate a clinical level of information in order for clinicians to assess the user recoveries as well as the user severity of the neck-related diseases. So in this case, it features a Bluetooth to capture both the optoelectronic signals as well as the gyroscope sensing information simultaneously, and sending into a cloud computation stage that can host a machine learning algorithm to analyze those heterogeneous data in order to generate assessment of the user to enable recommendation from the clinical personnel to the patients to optimize the rehabilitations in real time. So before the machine learning analysis, so the data will be fed into a pre-processing step, which will consider the sensing information from the gyroscope in order to remove the motion artifacts. As you could see, the initial data is confounded with the sufficient noise, which could come from the neck rotation as well as the body motions. And after the pre-processing and using the autoencoder as well as the Butterworth filter, we can generate a very stable baseline and consistent signal signatures that represents each movement that related to the neck muscles. And here shows an example of the pre-processed data, and you could see the each signals shows is a signature patterns that uniquely corresponding to muscle movement, including the breath, swallow, and even the coughing. And we can further using machine learning model to analyze the severity or amplitude of those targeted muscle activities. And here shows a video to show it's a real-time operation of the device. So the device is wirelessly controlled, and the data is sending to the laptop in front of the users. As you could see, as the user taking deep breaths, and the sensing signals shows well-defined signature patterns that correspond to each movement of the neck. And when the user is undergoing certain body motions, which is shown and later on, it captures such a body motion from the gyroscope, and also generates a confounding effects to the optoelectronic sensing signals. But we can using the pre-processing algorithms later on to counteract such motion artifacts accordingly. So here we probably just skipped this demonstration and fast forward to the analysis. So in this case, we are using a generic recurrent neural network to classify the neck muscles. So due to the heterogeneity of the sensing information, so certain channel came from the gyroscope, and the rest came from the optoelectronic components. We are using the dual channel recurrent neural network in order to providing very faithful results of the machine learning analysis. As you could see, the accuracy is acceptable, and the machine learning can label each events of targeted muscle activities. So which will allow us to calculate its occurrence frequency as well as intensity for later analysis. And we also compare the wearable devices with the state of art. One is the EMG. As you could see from the picture, the device, the EMG, is very bulky and not comfort to wear. But the sensing information shows a good correlation with what we have received from the wearable optoelectronic sensors applied on the neck. And then the other golden standard is using the video stroboscopy, and which providing a camera recording imaging level of information from a catheter that is inserted through the throat. As you could imagine, it's very uncomfortable, and it cannot be operated for a long time. But the recording shows a good correlation between our non-invasive wearable devices as well as such a semi-invasive catheter endoscope from the throat. So another advantage for the wearable devices is a real-world operation and during the daily activities. Here we demonstrate the user can wear the devices while play basketball. As you could see, the sensing signals show very strong motion artifacts from the gray data recording lines. And but still, the machine learning algorithms, the gyroscope could alleviate the motion artifacts, and the machine learning algorithm will be able to label the events of our targeted muscle activity from the neck regarding its coughing or other certain activity, as well as a deep breathing as well. So, and we can using the model to analyze its possibility of such events at a specific time point, which can be later utilized for analysis of the rehabilitation process. So it can not only use for patients with specific neck disorders, but also it can be applied to other part of the body for users for athletics to optimize the muscle training as well as a real-time monitor its muscle recovery process. So those are potential directions we are looking into to utilize those optical-based muscle tracking wearables. And then that concludes so the whole presentation. So we starting with the materials design and the structurings in order to integrate multiple materials coherently in a single devices platform and utilize the device to address a specific challenge in the biomedical space. So with that, I would like to acknowledge our team, and all the group members. So they are the engine of all the research efforts and realize all those research achievements. So I'm just here talking about their achievements. And finally, thank you very much for your attention.
Thank you for the fantastic talk, Professor. Couple of questions. You mentioned about near IR that can go deeper. How deep can it go?
Yes, depends on the intensity of the near IR. So for a tissue acceptable intensity, it can reach to several millimeters. And some literacy is around 2 millimeters, but others reach to 5 millimeters. Based on our benchtop test, I feel 3 to 5 millimeters, it can be very feasible through the near IR. The light. Beyond that, it requires a higher intensity, and then it comes to a biocompatibility issue, whether the higher intensity will generate additional heating effects to the skin that can damage the skin tissues, which could be another concerns in this case.
So a lot of people use inductive powering, magnetics, or even ultrasound for powering implantable devices. Do you think we can use near IR to power devices?
It's possible to use the near IR with a higher intensity. So that requires the near IR to be operated in a pulsation pattern that can minimize the local heating generations. And it depends on the location of the tissue as well. And a certain part of the tissue of the body has a higher near IR transparency than the other. I think that's also could be a consideration.
How do you convert light into a battery or power source? Can you do that? Is that possible?
Yeah, into a light source. So if converting light into electricity, so the conventional optoelectronic components would be capable. So the photodiode can convert the light into the electricity. Although the efficiency, I think, is also another concern. I think that the highest efficiency of such light electricity conversion is only 30%, and which means there's a limitation on that, which also defines the implantation depth of such device as well. Yeah.
Thank you. Another question is, you mentioned about gyroscopes. Are these flexible or rigid or commercially available, or are you making them?
Yeah, also good point. So the gyroscope is commercially available. The chip itself is not flexible, but it's not significantly big. So in this picture, so the middle black red box is the corresponding to the gyroscope. which you could see from the footprint, is a relatively small. It's a couple of millimeter in the lateral dimension, which in this case is acceptable.
Thank you. Thank you. Are you working on implantable devices, and how about biodegradable versions?
Yes. So those are ongoing projects, and which is not present here. We are also working on the degradable materials, both degradable hydrogel as well as some functional degradable materials that can be magnetically actuated, as well as using optical way of actuation, especially for the 2D maxing. It has a strong absorption of near infrared light, which and also is about compatible. We can functionalize the surface chemistry to make it in a biodegradable in a certain way, and that could be a basic building blocks for making the implantable devices.
Thank you. The drug delivery microneedles, are they reloadable or is it a one-time usage?
Yes, that's also a great point. So in the situation, the case present here is not reloadable, which could be a challenge for certain scenarios. And so in our ongoing projects, we are designing a hollow probes that can be electrically actuated, which can satisfy the reloading purpose, which is not present here. So it's not yet summarized into a manuscript yet.
Thank you. Another question is brain. The brain, as you mentioned, is a soft tofu tissue, but the skull is extremely rigid. So a polymer needle cannot penetrate through the skull. What strategies are you using to be able to probe the brain?
Cool. Yes, that's a practical concern. And in this case, we haven't providing a specific engineering design to overcome the skull layers. It follows a very traditional method using a drill to open the skull, and then we can inject the polymers. And for the needle shown here, so the mechanical rigidity is sufficient to penetrate into the tissue. But for other purpose, if the probe is a sufficient soft, it also requires additional guiding biodegradable materials to providing the mechanical rigidity for the insertion. And after inserted, the backing layer can be dissolved and leaving the soft probes in the brain to ensure the biocompatibilities. So for the skull implantation through the skull, we haven't providing additional design mechanism to overcome yet.
Thank you. Great presentation and amazing progress. How does the therapeutic efficiency of microneedle-based drug delivery compare to conventional drug administration routes such as intravenous injection or oral delivery?
Yeah, so the comparisons is a critical question. I think that the fact is we haven't providing a thorough comparisons, and so but there's a certain characteristics for these devices that can be differentiated from the traditional device delivery drug delivery mechanisms. So one is the dosage. So in this case, as you could see, each needle has a certain small volume, and that can limit the dosage of each drugs. But we can also design a collection of multiple needle to initiate the drug delivery simultaneously in order to increase the dosage for specific dosing schedules. So that could be one mechanisms. And the additional advantage for this is we can manipulate the location of the drug delivery from the device contact areas. So that could be useful for a wound healing process. In that situation, we can specify the needles that more close to the targeted infected wound location to release drug, and having other location in a standing by areas depends on the wound healing process. So these could be another special capability for the special scenarios. So I think that could be the difference in general.
Thank you. Does the use of longer needles increase the risk of pain or other adverse effects during or after administration?
Yeah. So the question will be the longer needle to reduce the pain from.
No, increase the pain, or do they have a problem with breaking or other problems?
Yes, that's also a very practical concerns. And in this case, so the needle matrix itself is bioresorbable polymers, PLGA, and it has a certain rigidity, and also it can become relatively soft upon contact with the biofluid. So that can minimize the breakage of such needles compared with other plastic based or inorganic silicon-based needles. It's less vulnerable to the fractures. And in terms of the pain, so the microneedle can outperform with those traditional hollow needles that has been used on the market to inject insulin or to deliver the drugs transdermally. But I think the pain depends on the individual cases. It still exist and may not be as good as those non-invasive mechanism of drug delivery.
Thank you. What protective mechanisms are in place to prevent or mitigate adverse effects in the event that the microneedle device breaks and causes an unintended burst release of the loaded drug?
Yes, yeah, that's also in terms of the breakage of the drug needles. One safety concern will be the gold-coated layers, which is robust to prevent the drug diffusion to the externally, and that can alleviate the scenarios where the fractured needle release excessive drugs to the tissues. And then for other breakage tissue scenarios, I think this particular device would shows no better capability compared with other microneedle devices as well. And one advantage, I think, as shown in the paper, is the needle itself is using the PLGA, which is slightly rigid, but the base of the needle is using PVA, and that shows a good flexibilities, which indicates the platform can be relatively flexible. It can be conformed to the skin. That can prevent the risk of breakage to a certain levels. Yeah.
Thank you. One other question is, in the design of stimuli responsive robots, how can shape or structural transformations be precisely controlled to accommodate the specific mechanical and biological characteristics of different tissues or organ environments?
Yes, so there's a lot of performance parameters involved in design the hydrogel actuation layers. So one is the activation temperature. So in this case, we are using the stimuli responsive hydrogel PNIPAM and PAA block copolymers. So by controlling the blocking ratio between the two monomers, we will be able to modulate the activation temperature for the hydrogel. If we can position it right at the physiological temperature or slightly above, that can allow us to using additional heaters to trigger the activations. And then the precise control of each activation step is through the heating amplitude, which can be captured by the sensors from the artificial skin layers, which can to form a closed loop mechanisms to guide the thermal heater heating amplitude to control the actuation amplitude accordingly. So those kind of considerations. And then the actuation geometry can also be controlled by the interplay between the artificial skin layers as well as the hydrogel muscle layers. So in this case, the blood vessel cuff, we can have in the strips structure pattern on the skin layers to enable a twisting configuration of the structural transformation instead of a conventional bending. So those are some mechanism for us to enable structural control for the muscle.
Thank you. One other final question is, this person says, I don't know sensors. What is the general challenging questions in the sensor field using cardio organoids?
Cardio organoids.
Yes, I think you showed the real cardiac organ.
Yes.
And then what are some challenges in cardiac patches, sensors, and other things for that?
Yes, yeah, that's also a great questions. So the sensor design is more a challenge, mostly at the materials levels. So especially for the heart, which will undergoes dramatic mechanical deformations. So that requires the sensor to be sufficiently stretchable as well in order to match the mechanical deformation. And also for the heart, especially for the ECG sensing, which requires the transport of the charge carriers across the sensor tissue interface. And if having a abiotic sensor attached on the heart, over time, it can generate fibrotic tissues for non-compatible materials. So that can damage the functionality of the device. So which indicates the sensor itself requires sufficient biocompatibility in order to prevent fibrotic tissue generations. So which highlights the advantage of using hydrogel in the cardiac sensors to minimize the fibrotic tissue generation. So hydrogel has been demonstrated by many research groups on the advantage of biocompatibilities. So in this case, so which is also a reason we are aiming using hydrogel both as the actuation matrix as well as the artificial skin layer matrix.
Well, that's all the questions. Thank you for your time, Professor. Truly appreciate it.
Thank you. Thank you for these opportunities.
Yeah, thank you. Bye-bye.